right, so this is going to go on page 65 when we're done. And I'm not sure if I said this yesterday or not, but we got halfway through Unit 2 before Christmas. We're going to pause on Unit 2 for a little while. We're going to do a little bit of stuff to get us started in Unit 3 because there's some things that we have to know and have down pat before we start Unit 3. So we're going to do a little bit of trig stuff. And then we're going to practice it while we finish Unit 2, and then we'll be ready to go when we get to Unit 3. Okay? So we're going to start with kind of a review of some trig stuff you already know, and then get into some of the newer stuff that we have to make sure we know pretty well before we start Unit 3. So I started by giving you the Greek alphabet. I'm not going to read this to you. You can read it at your leisure, but here's the first part of it. Because when we move into trig, our, your basic unknown algebraically is usually x. And if once we've used x, if we need another one, we usually move on to y and z. Of course, we can use any letter, but that's just kind of what happens. So when you're talking trig and looking at angles, theta becomes your basic unknown angle. If you've used theta and you need another one, we generally move on to alpha and beta. But again, we could use lots of different ones. Except for in the Greek alphabet, some of them actually represent something else, and so it wouldn't make as much sense to use them. But here we have alpha, beta, gamma, delta, epsilon, zeta, eta, and theta. And you should recognize the capital delta means change, and these are universal math and science. Change, you've probably seen it in chemistry or physics. At the beginning, or closer to the beginning of the year, when we had numbers or an element, we use that little symbol. It's actually epsilon that the name and some of them have multiple pronunciations. It's a tomato type of thing. I think these on this page are that's pretty much the only way to really say it. The rest of it here, iota, kappa, lambda, mu, nu, psi, omicron, pi, you should definitely recognize pi, rho, sigma, tau, upsilon, or upsilon, phi or phi sometimes, chi, psi, and omega. So alpha and omega, the beginning and the end. I think that's something that, you probably have heard before. We should all be familiar with the lowercase pi. Anybody know anything about lowercase tau? Okay, tau is actually 2 times pi. That's what that represents. So, and there's applications to a lot of this. Sigma, the summation notation. So I had to memorize the alphabet, the capital, lowercase, the names and the pronunciations for one of my math classes in college. If you rush for a sorority or fraternity, they may make you learn it because the capital letters are used to signify those. But I just want you to see what they are. I wanted you to be exposed to it. I'm not going to test you on it or anything. I am going to play for you, though, the Greek alphabet song. So if you do ever have to know it, then you could find it on the YouTubes.
Alpha, beta, gamma, rays, delta, epsilon, hey, 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 zeta, eta, theta, iota, then there's kappa and lambda, mu and u and xi, xi, omicron, and then there's pi, rho and sigma and tau too, upsilon, it starts with u, phi and chi and psi are fun, omega, and then you're done. Learn all that and then you're set. That's the whole Greek alphabet.
Earworm for today. Maybe I'll send it out to y'all in a remind, and then you can memorize it if you want to. But the YouTube didn't exist back in the day, so I had to make up my own song. But it was similar to that, I guess. So that's just going to go in your ISN. It was just for informational purposes. Let's move on to this. This is going on page 66. So back in October, before you took the PSAT and the SAT, I took these notes and chopped them up and put them together with some other things. We did a crash review course in right triangle trig, and then I threw in some extra stuff to see what might stick a day or two before the test. In hindsight, I should have done it sooner and a lot different and better, but it was sort of a last minute thought. So it is what it is at this point. But because we've already talked about some of this together, I'm going to go through it probably a little bit more quickly than I normally would, but go back through it with you. All right, so trigonometry. You learn right triangle trig in geometry, level of geometry you took. Trigonometry, or trig, is the study of the relationships among the sides and angle measures in triangles. It literally means triangle measure, trigonometry. So with that, we have trigonometric ratios, and mathematically, a ratio usually should make you think of a fraction. Set up some sort of little ratio. It compares the lengths of two sides with respect to an acute angle. So if you have a right triangle, you have one right angle, the other two angles have to be acute because they're going to have to add to give you the rest of the 90 to get the rest of the 180. And we usually call it theta. Okay? Then we have trigonometric ratios and a trigonometric function. That's just a rule defined by the ratio. So sometimes trig ratio and trig function are kind of used interchangeably. They're technically not the exact same thing, but they can be used interchangeably just fine. So can you use trig on triangles that are not right triangles? Yes, but you don't know how yet, and we're not talking about that right now. So as far as we're concerned, we have to have a right triangle. Okay, that's just how it's going to work right now. And so when you look at right triangle, I have a right angle. That's all I need it for, is to say, hey, this is a right triangle. And then that's never the angle that you, quote, use. You use one of the acute angles, and it's usually pretty obvious which one. Like in this case, it's labeled, or you'll be told or something. It won't be a difficult decision. But here's my angle. Across from the angle is the opposite side. So we're going to label it with an O. The hypotenuse, because we've already had this discussion, yes, it is the longest side, but we don't have side links. We don't get to go by the way it looks. The actual definition of the hypotenuse is that it's across from the right angle. That's what makes that the hypotenuse. And then this is the adjacent side. Okay? So there are 6 trig ratios. You learn 3 of them in geometry. The other 3 are just reciprocals. So once we know 3, we really do know all 6. To get the 3 that we already know, we have an acronym to help us. What is that acronym? SOHCAHTOA. Good. And just like any acronym, it doesn't help you any if you don't spell it correctly. So it's SOHCAHTOA. SOHCAHTOA. That helps us set up these ratios. So we have sine, cosine, and tangent. Would I ever say sin, cos, and tan? No, because you sound like a moron, right? Just like if you go to the doctor and you have Dr. Smith, you don't say Der Smith, right? So these are abbreviations. We want to sound as intelligent as we are, or maybe more intelligent than we are. I don't know. All right, so the way we use SOHCAHTOA, this means that sine is opposite over hypotenuse. That's what this is. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. Okay, that's all old business. So then we have the 3 reciprocals, cosecant, secant, tangent. So the sine, cosine, and tangent are each paired up with one of the reciprocals. Tangent and cotangent are reciprocals of each other. That makes sense, right? So that if this is opposite over adjacent, cotangent is adjacent over opposite. And then every pair has one co in it. So we have tangent and cotangent. So when I try and figure out what sine goes with, sine is not going to go with secant because then there's no co in the pair. Sine goes with cosecant, which makes this hypotenuse over opposite. And then cosine goes with secant, which would make it hypotenuse over adjacent. Okay? There is no need for an acronym for the reciprocals because we should look at the reciprocals through the lens of the original 3 every time, okay? That's the way I do it too. If I'm going to use cosecant, my first thought is Cosecant is the reciprocal of sine. Sine is opposite over hypotenuse, so cosecant is hypotenuse over opposite, right? We just do everything through sine, cosine, and tangent, and you're not learning, you don't have to remember twice as much. Okay? Everybody good so far? All right, so then we have reciprocal functions. Now remember your ratios and your functions, they're kind of used interchangeably. But it does say cosecant, secant, cotangent ratios are the reciprocals of sine, cosine, and tangent. They are called the reciprocal functions. So yes, cosecant is hypotenuse over opposite, but another way to look at it is cosecant is the reciprocal of sine, so it's 1 over sine theta. Secant is the reciprocal of cosine, so that's the same as 1 over cosine theta. And cotangent would be 1 over tangent theta. Now, we talk about sine, cosine, and tangent, but you're always taking sine, cosine, or tangent of an angle. So I would have to have sine of 30 degrees. Sine by itself doesn't make any sense. Just like square root sine by itself doesn't make any sense. It's an operation. Square root of what? So it's always sine of theta or sine, cosine of theta or of x or of whatever it is. Okay, everybody good? All right, so we're going to come up with, we're going to find the exact values of the 6 trig functions of theta. Now, exact values, none of this is calculator based anyway, but even if it was, it would not be the decimal that I would get at the end. It would be the answer that might look a little ugly to you. I mean, an exact answer can be 5 or 1/2, but it would also be like the square root of 2 and not the decimal that would be that. All right, so exact values, here's my theta. So across from theta, I'm going to label this as the opposite side. Across from the right angle, it's my hypotenuse. This is adjacent. Okay. Then I'm going to set up my ratios. Sine is opposite over hypotenuse, so I'm going to put 4 over 4 square roots of 5. And then I've got to reduce it and make it legal. So to reduce it, I can cancel those 4's out. It's going to give me 1 over the square root of 5. Right? But is it legal to leave a square root in the denominator? No, it is not. So I need to rationalize the denominator. So I'm going to come over here and we're going to do the work once, but I'm going to do it every single time. If I have 1 over the square root of 5, to rationalize the denominator, I have to multiply it by a fraction that has a value of 1. Okay, so square root of 5 over square root of 5, that would be 1, which means I'm not changing the value, I'm changing the way it looks. Multiply straight across gives me the square root of 5 over, what's the square root of 5 plus the square root of 5? 5. And I can't cancel those out because they live in 2 different worlds. That's my answer, square root of 5 over 5. Okay. So look, 1 over the square root of 5, when you rationalize it, becomes the square root of 5 over the square root of 5. If I have 1 over the square root of 7, it'd be the square root of 7 over 7. 1 over the square root of a monkey would be the square root of a monkey over a monkey. Like it's the exact same thing every time, so there's really no need to go do the work every single time. Okay? We good on that? All right, perfect. So then cosine. Cosine is adjacent over hypotenuse. 8 over 4 square roots of 5. So I can reduce that to 2 over the square root of 5. And then hopefully you've done square roots enough that you don't necessarily even have to write it down. You can even picture it in your head. I'm multiplying by the square root of 5 over the square root of 5. This becomes 2 square roots of 5 over 5. Everybody good so far? All right. Tangent, opposite over adjacent. That's 4 over 8, which gives me 1/2. Now that I have those 3, I can get my reciprocals in. So cosecant is a reciprocal of sine. So this is going to be 5 over the square root of 5. So let's come over here just once and do 5 over the square root of 5. I'm going to need to rationalize it. Okay. Okay. So then this gives me 5 square roots of 5 over what? Can I reduce that? yeah, I can cancel those out, and I'm just left with the square root of 5. Now, and maybe this is what you were thinking, but these three things here, these are all equivalent, right? They're just different forms of it. So when I went to take the reciprocal, I didn't have to use this one. I could have used this one. And then if I just take the square root of this, I get this. But I wanted you to see that you can do all that work and go from here to here or from here to here, or you can just kind of understand how they're going back and forth and how they work. Okay? What questions you got? Jenny, you still have a question? I don't believe you, but okay. So when I'm going to do the secant is the reciprocal of cosine. I could do the reciprocal of this one, but wouldn't it make a little bit more sense to do the reciprocal of that one? Square root of 5 over 2. And then the cotangent would be 2. Okay. What questions do you have? Anything? All right. So number 2, here's my angle. This is my opposite side. Across from the right angle is the hypotenuse. This is the adjacent. Now, I don't know the hypotenuse. I need to find it. What process could I do to find it? What? A square Pythagorean theorem? Yes, learned in 7th grade. Pythagorean theorem. All right, so that means I can do 6 square root of 3 squared plus 6 squared equals h squared. Now, what I wrote down is not 100% how we should write it. I'm sure that's how most of you probably write it. Then some of you would solve it correctly, but we really should have parentheses right here, because what is happening is we have a times b squared, which gives you a squared times b squared, because we don't always handle this appropriately. So when I do this, that means I'm going to square the 6, and then I square the square root of 3, and what do I get? 3. Okay. Plus 36 equals h squared. So that's going to be 108 plus 36 equals h squared. So 144 equals h squared. So h is 12. Technically here you get plus or minus 12, but it's a side link, so we just use 12. And then I can set up my ratios, okay? If you notice that the way they are labeled, it makes it a special right triangle, then you would just know that the hypotenuse is 12, but not everybody's going to recognize that, so then we have to be able to do Pythagorean, okay? All right, so then set up my ratios here. Sine is opposite over hypotenuse, so that is 6 square root of 3 over 12. And then I can reduce that to square root of 3 over 2. Okay. Let's go ahead and do the reciprocal, which is cosecant. That would give me 2 over the square root of 3. And when I rationalize, what would I get? 2 square root of 3 over 3. Cosine adjacent over hypotenuse, 6 over 12, which gives me 1/2. So secant would be what? 2. Tangent, opposite over adjacent, so 6 square root of 3 over 6, which gives me the square root of 3. What is the reciprocal of the square root of 3? Okay, 1 over the square root of 3. We can write that, and then that becomes square root of 3 over 3. And it's okay once you understand the patterns to go straight from here to here. That would be totally fine. Okay. What questions you got? Anything? All right. So this next one, they didn't give us a triangle, we just have a trig value. So we know that the tangent of theta is 7 over 24, which means the cotangent would be 24 over 7. And we got 2 of the 6 filled in. I know that tangent is opposite over adjacent, but I need to figure out the hypotenuse so that I can figure out the other two. I'm going to draw myself a triangle, a right triangle. Doesn't have to be to scale or anything, and pick an angle. You're drawing it, it's totally fine. Here's my angle that makes this the opposite, the hypotenuse, and the adjacent. Then I know that opposite over adjacent will be 7 and 24. Now, I don't necessarily know that those were the actual side lengths that gave me that ratio. Okay, so I want to make sure that we can understand why these ratios work. So we're going to come back over here first and look at this. I'm going to redraw this same triangle here, right? And then here's my theta. Instead of using the numbers that are there, I'm basically going to do kind of what we just did and use my answers to label it. So if tangent is opposite over adjacent, that's 1 over 2. So opposite would be 1, adjacent would be 2. And then when we did the hypotenuse, if this is opposite over hypotenuse, right? Opposite over hypotenuse right here, then this would make this the square root of 5. Now, those aren't the exact same side lengths that I started with, but do you see that if I took these, one of them by 4, I would get this? Because the triangles are similar, and with similar triangles, all the angles are congruent. That's what makes them similar triangles, right? Does that sound familiar? So that's why this stuff works. If I put adjacent and get 1/2, it's 4 over 8 or 1 over 2, then whatever this angle is going to be the same for each one of them. I don't know what it is. I just know that they're the same, and that's how trig ratios work. So even though I don't know for sure what my side lengths are, this is what they reduce to, so I'm fine. So then I got to find the hypotenuse. I can do Pythagorean theorem again. Go ahead and tell you that when you do that, this is a Pythagorean triple, which if you know them, great. If you don't, then you have to do Pythagorean theorem. It's okay. Most of you probably don't know them. So it's fine. It's not worth taking up space in your brain. But with that, then, you should be able to set up those other 4. So go ahead and write in your other 4 ratios there. All right. Any questions? Easy when you don't have any square roots, right? Okay. So on number 4, they gave us that secant of theta is 4. So I can put that in here. I make that into 4 over 1. Means this would be 1 over 4. I know that cosine is adjacent over hypotenuse. So this is hypotenuse over adjacent. And I can, once again, draw my triangle here. So opposite, hypotenuse, adjacent. And so this is 4, this is 1. And then you go ahead and find that missing side on your own. All right, so Pythagorean theorem should be able to do it quickly and efficiently and correctly. Get the square root of 15. And then go ahead and see if you can set up the other ratios there. Any questions at all? All right. Then we're going to look at special right triangles again. So we talked about these quickly and reviewed them quickly in October as well. We did not do the rest of what's on here though. So when you have these two special right triangles, 30, 60, 90, 45, 45, 90, there's different ways to teach them. Some people use X's. I think that's a bad idea. So I like to use the S's for S for short leg and L for leg. But on the PSAT and SAT formula chart, they use S's for the 30, 60, 90, and they use X's for the 45, 45, 90. So one of the things I showed you was to go on that formula chart and mark out the X's and change them to S's. So we'll just use S for everything. But in the 30, 60, 90, S really represents the short leg because you have two legs, a short leg and a long leg. Your short leg's across from 30, long leg's across from 60. So across from 30 is the short leg. Hypotenuse is 2 times the short leg, and the long leg is the short leg times the square root of 3. Right? For the isosceles right triangle, or the 45, 45, 90 triangle, you have 2 congruent legs. That's why I like to use the L, but S for side, I guess. So these would both be S, and then this would be S times the square root of 2. For the purposes of what we're going to do, we could have, we could leave the S's in there and do that, but to simplify it a little bit, make it a little bit easier for ourselves, we are going to basically substitute 1 in for S. Let's pretend like S is 1. If S is 1, then this is 1, this one is 2, and this is the square root of 3. And over here, this would be 1, 1, and square root of 2. And that's another way to teach it with the ratios, which I think is even a worse idea, but who knows? I have no idea how you've seen it in the future. But basically, we're going to use those green numbers, because that's how the ratios work, to come up with these ratios, right? We're going to start, we're just going to do this a little piece at a time. So we're going to do sine of 30. So here's 30. Opposite over hypotenuse, that's going to be 1 over 2. Cosine of 30, adjacent over hypotenuse, that's the square root of 3 over 2. And then tangent of 30, opposite over adjacent, that's 1 over the square root of 3. But when I rationalize that, that becomes what? Square root of 3 over 3. Good. And then we'll just mark that one out so we have less to look at. And then we're going to pause right there for a second, right? So we have found the sine, cosine, and tangent all of 30 degrees. Now we're going to go back to sine, cosine, and tangent, but do it for 60. So now I'm looking at this 60-degree angle. For sine, that's opposite over hypotenuse. That's the square root of 3 over 2. Cosine of 60 is adjacent over hypotenuse. That's 1 over 2. Tangent of 60, opposite over adjacent, that's square root of 3 over 1, or just square root of 3. And then I want you to look at those 6 numbers that we just wrote down. Even though we just wrote down 6 numbers, there's only 4 different ones, right? These 3, and then the square root of 3. And I want you to see one of the many patterns we're going to see in all of this, because eventually, not today and not tomorrow, but you're going to have to just know these. If I ask you, what's the sine of 30? What's the cosine of 60? You're going to have to just know them. I do not want you to go home and try and memorize them. I have a slow process that I'm going to take you through where we actually learn it, and it's not going to be that big of a deal. But I want you to see the patterns now, because it's going to look overwhelming. Like a lot of what we do, once we're done, if you look at it, you're like, wow, that looks bad, but it really wasn't that hard. I want you to see that it's not 1,000 different numbers you have to know. You just have to know how things relate and where the pieces go, and it won't be that bad. But see how the sine of 30 is the same as the cosine of 60? Right? So that's going to happen every time in a triangle. The sine of one angle is the cosine of the other angle, because all that's happening when you change them is you're changing what's opposite. So these two just switch places when you have those the angles from the same triangle, right? Now let's go in and do our reciprocals. So cosecant is the reciprocal of sine, so cosecant of 30 is going to be 2. Secant of 30 will be 2 over the square root of 3. But when I make that legal, that becomes 2 square roots of 3 over 3, right? And then what's the reciprocal of the square root of 3 over 3? Square root of 3. So then cosecant of 60, it would be the reciprocal of this. Well, we just found that right here, 2 square root of 3 over 3. Plus, if sine and cosine switch places, then it would stand to reason that cosecant and secant would just switch places, right? So without even looking at what the cosine of 60 is, if the cosecant of 30 is 2, then the secant of 60 should be 2. And then the reciprocal of the square root of 3 is the square root of 3 over 3. So you're going to start to see, and I'm going to point out a lot of, when we go through this, a lot of different patterns that we have and how all this stuff works together. Okay? We all good at this point? All right, so now let's do 45. So the sine of 45, I need opposite over hypotenuse. They're both 45-degree angles, so I'm just going to pick one. We'll just pick this one. Do opposite over hypotenuse. That is 1 over the square root of 2, but that's not legal. That should be square root of 2 over 2. Right? All right, so then cosine of 45, that's adjacent over hypotenuse. That's also 1 over the square root of 2. So that's square root of 2 over 2 again. Now, does it make sense that the sine and cosine of 45 are the same? It should, right? Because the two angles are the same, so they have to be the same. Your opposite and adjacent are the same thing. Tangent, opposite over adjacent, that's 1 over 1, which is 1. So then cosecant, the reciprocal of sine, the reciprocal of the square root of 2 over 2 is square root of 2. So secant of 45 is also square root of 2. What's the reciprocal of 1? 1. Oh, thank God. All day long I've heard 1, and I'm hoping to make it the whole day because I almost always hear -1 and 0, and I don't know where those are coming from because they make no sense, but I've heard 1 all day, and I'm just very thankful. So as of right now, what you should be able to do, if I ask you what is the sine of 30, the cosecant of 60, you should be able to set it up from special right triangles, not just know them. We're not there yet, okay? But you need to know how they are related because these are all values that are going to become very, very important to us. And your assignment is in Delta Math. So if you need more practice rationalizing because you feel like I'm doing magic up here, you got it in Delta Math and you can just practice away. All right, and just setting things up and understanding your ratios. So the majority of what we did here should have been a review. I know that the reciprocals are new to you, but we're going to start strong, right? Which means today you do your Delta Math. Okay, promise yourself that you are at least going to get it started, and we're going to start strong and not be a bunch of slackers, right? All right, good deal.